Hi there, this is Mladen Jovanovic from Complementary Training, and in this video I'm going to share some of my random thoughts on injury prediction, especially distinction between association and prediction, confusion matrix, cost, and making decisions based on prediction. So this video is influenced by a recent publication by Tim Gabbett, particularly this graph, which shows the famous J-curve, showing the relationship between acute and chronic ratio or training stress balance and likelihood of getting injured. This graph is recently referenced a lot in some of the publications, and I want to offer some of my opinions on this one. The way the acute to chronic is calculated and what variables are being used, what's the unit of analysis, is it a week or is it a day, is really important, but it's not so important in this particular video. And same thing for a likelihood of injury. So is that an injury happening in this week or next week or next 7 days or whatever? So these two are really important, how we estimate them. But for the sake of this video, we're just going to assume these are valid and reliable features that are useful in practice. So I'm going to use R to simulate some of the data. I'm gonna start really I would say simply with a concrete example, and then proceed with the analysis. Anyway, the thing that we need to remember for this figure is that we have a sweet spot, which is the area where we have the least probability of getting injured. The numbers here, so one is when we have same acute to chronic ratio, and the likelihood of subsequent injury. So the numbers are 5% to 25%, and I'll show you how is that calculated actually. And then you remember the shape of the curve. So that's pretty much it. So I'm now going to switch to R, and I'm going to generate some of the data. So I'm just going to load libraries, and we're going to have 100 athletes in each zone. And by zones, I refer to the zones training stress balance zone. So zone 1 is between 0.3 to 0.8. Zone 2 is from 0.8 to 1.2, and from 1.2 to 2.5. So this is simulation. So this is the data generated by a code, and in each zone we generate 100 athletes with a given probability of getting injured. So in zone 1 we have 25% probability of getting injured. In zone 2, so the green zone, we have 5%, and in zone 3 we have 3%. So I'm gonna bind all those three into one data set, and I'll show you. And I'll show you how that looks. So we generated 239 healthy athletes and 61 injured athletes. So the data frame looks like this. So we have an injury, so 1 for injury, 0 for non-injury, and say we have injury tag, which is injured and healthy, and training stress balance. So as you can see, we have 100 athletes in each zone. So the data frame is 300 rows big. So this is all zone 1, and now we are switching to zone 2. We can see higher training stress balance numbers and so forth. So as I said, it's 300 cases, 300 athletes, 61 are injured, and 239 are healthy. So this is going to look much better when we plot this. So I'm going to use ggplot. So what we have here is this is the distribution between injured and healthy based on a training stress balance. As you can see, there's a big overlap, and between the classes. And we also plotted two vertical dashed lines that represent the border between zone 1, zone 2, and zone 3. So what we are trying to do with the model is to get the probability of getting injured based on a training stress balance. So we are using these numbers to get the estimate of the likelihood. So the more athletes we have here, pretty much counting, we're gonna be most likely to get injured. The way we're gonna fit that, we can use a linear regression, but linear regression can jump over 1 or 0, so we need to constrain it between 0 and 1, and that's why we are using logistic regression, which is pretty much gives us the sigmoid function, which is looks like S. So it goes from 0, climbs up, and goes to 1. So for example, if we only have full overlap, so the function might look like a linear trend, because there's no zones where we only have injuries or only have healthy athletes. If we have only injuries in for example, a particular area, then that function is going to jump up all the way up to 1. I'll show you quickly how that looks. So that's the same graph with confidence interval, 95%. And we can see the likelihood of getting injured. As I said, plotting things like this gives you a little bit of idea how this function is estimated. So the more guys got injured here, this is gonna jump up higher. So that's pretty much it. It's just counting the dots. And here we have, I didn't explain beforehand, we have a jitter. So jitter is like a, because all these guys are gonna stay on a one line, I put the jitter, which would give some a little bit of randomness, so we can see the distribution and avoid the overlap between the dots. So injured are red and triangles, and healthy are green and round. The other function, as I said, this looks like a linear function, but it's actually really stretched out S curve. So it looks like letter S. And now we're gonna use a polynomial fit, which gives us a J curve. So what goes into a formula, into a model, is a training stress balance and training stress balance squared, and this gives us the famous J curve. So in this area we have highest number of healthy athletes and least number of injured, and the ratio is changing when we switch the zones. So that gives you hopefully some idea of how the function is generated. It's quite simple, it's pretty much counting, so at least that's how I look at it. Another way to plot this distribution is to use is to divide the distribution based on a healthy or not. So we want to plot the distribution of training stress balance first of all. So that's probably going to look like a normal curve. So distribution of training stress balance. But if we split that into healthy and injured athletes, we're going to get this. So we also again get the overlap. As we can see, the highest number of healthy athletes are in this zone 2, and then we have 2 spikes of number of injured athletes in zone 1 and zone 3. So that's slightly different way to show you the distribution of the classes. So what we want with the prediction, if we want to minimize the overlap, so that means the performance of the classifier, in this case a model, is going to be better because the classes will be separate. And I'm going to show you how to estimate that performance of the classifier, or in this case a model. So the first thing we're going to do is going to use a normal logistic model. So we're going to use training stress balance to predict injuries. And as I said, injury is a class. So in this particular case, it's 0 and 1. So we are using binomial and binomial distribution and logistic regression. So we're going to build a model. And I'm going to show you the summary. So as we can see, what we are looking for are the parameters. And similar to linear regression, logistic regression, we also have an intercept and training stress balance. As we can see, training stress balance is associated with injuries, as can be seen from this picture as well. So it is associated, and it's significantly associated because the slope is bigger than 0. Hopefully that's understandable. What we can do also, before plotting we can also plot the confusion matrix. So the confusion matrix gives us pretty much the counting of misclassified and correctly classified cases. At the top we have the real healthy athletes. So we have, if I remember correctly, 239. Let me just double check. So yeah, we have 239 healthy athletes and 61 injured athletes in our data set. But using this logistic regression, and in this case using a threshold of 0.3, so everything above threshold 0.3 you're going to call injured, and everything below that or equal to that we're going to call healthy. So now we are checking how the model is performing, and diagonals are correctly classified classes. Everything off the diagonal are the errors. So we have a false positive. In this case, we're gonna classify. This is false positive. We're gonna classify someone as injured, and he is actually healthy. And we have false negative, which is this. We're gonna call someone healthy, and he's injured. So these are two errors we are making. And lately I'm going to expand that they might cost us differently, and we might use the different cost to optimize finding the best threshold. As I said, the threshold is between 0 and 1, and we can play with selecting the threshold to give us the optimal number of errors. So the number of diagonal is going to stay same. So we might play with the threshold to distribute them differently based on a cost. How much does it cost us to make false positive or false negative claim? Let me see, where was I? Okay, so let's try another cost. So this is when we use 0.3, let's say 0.5. So with 0.5 we called everyone healthy, and let's just plot this first. So I'll show you the same distribution as before. So in this case, so injury tag are the real guys, so real healthy and real injured, and we are plotting the distribution of the prediction of the model. As you can see, there's a big overlap. So if you imagine a vertical line, so that's a threshold. Everything over that threshold we're gonna call let me just plot the line quickly. So I'll just do this. It goes like this. Let's see if this is gonna work. Okay, so I've selected the threshold 0.3, so everyone over 0.3 is going to be called injured. As we can see, we misclassify some of the healthy guys and we correctly hit some of the injured guys. And same thing, everything below 0.3 we might call healthy, and as we can see, we misclassified a lot of injured guys and correctly classified a gross amount of healthy guys. So what we can do is we can try to play with the optimal threshold. Ideally, and that's why we want a big separation or no overlap between the classes. So if there's no overlap between the classes, we can select the right threshold, and we minimize the number of the errors, in this case false positive and false negative. So one way to visualize the performance of the classifier or the model is to use a receiver operator curve, which is pretty much visualizing sensitivity and specificity, in this case how many correct injuries we identified, that's specificity, and how many healthy guys we identified, that's sensitivity, if I remember correctly. But that's pretty much the logic behind it, based on changing the threshold. So the receiver operator curve looks like this. One thing to remember is that a diagonal line is pretty much a random guess. Area under curve is the area under the receiver operator curve, and closer to 1 it's better. Closer to 0.5 means it's useless garbage. As we can see, the logistic regression is performing really poorly. So let's try a polynomial, so pretty much a J curve, and see how that's gonna perform with a receiver operator curve. So I'm gonna fit a logistic using a training stress balance and training stress balance squared. I'm gonna show you the summary. As we can see, they're both statistically significant, both training stress balance and training stress balance squared. They're significantly associated with the injury. So let's plot the distribution first. So again, I'm plotting the two classes, the two real classes, and the prediction by the model. So pretty much I'm plotting distribution of the model predictions, but I split them in two classes which are pretty much real. So the classes in the data set. As I said, I wanna see two separate classes, which means that the model is able to differentiate between two classes, in this case healthy and injured. Similarly, this model also cannot classify them correctly, but it's a little bit better. And looking at the first graph, it's impossible to expect the model to differentiate these two perfectly because they are not perfectly separated. So there's a big overlap. So we cannot expect really good performance of the model. So one of the points is that even if the, say, a feature, in this case training stress balance, is associated with injury, so that means that increasing, actually I cannot say that because this is not, this is only association, it's not causation. So the guys who are injured seems to have higher training stress balance compared to the guys who are not injured. So, and also in the opposite direction, so there's much more injured guys when training stress balance is increased. So that doesn't necessarily mean we can conclude the causality factor that increasing training stress balance is going to increase the likelihood of injury. And that's something to keep in mind as well, because most of the injury studies are pretty much observational ones. There's no intervention. So before we have interventional study, we need to remember that these are only associations. But the point is, even if we have association, the usability, the predictive power, is pretty much useless in this case. Let's see how this model, polynomial, performs. So we also have a confusion matrix showing the real healthy guys, the real injured guys, and the predicted healthy and predicted injured. As I said, diagonal is are the correct guess, and off the diagonal are the false positive and false negative errors. And by changing the threshold, let's say call this 0.1, we're gonna change the this distribution of the diagonal. So as I said before, we are playing with a vertical line, deciding where to put it. So we have minimize a particular type of error. We cannot make it more precise, but we can minimize a particular type of error. So it's pretty much trade-off between false negative and false positive by changing the threshold. And let's plot the receiver operator curve. So receiver operator curve is pretty much showing us this trade-off between sensitivity and specificity, or pretty much false positive and false negative errors in a graphical form. Again, area under curve is slightly better, so this model is pretty much more useful. It's able to identify two classes much better. As I forgot to say, actually, this model performance is based on a training data. So the data we use to feed into the model. In machine learning, we usually keep one data set as a holdout, and then test the performance of the model on that model that's unseen during the model build-up and tuning. And usually the model might overfit, and we might get slightly or much worse area under curve. So that's why it's important to realize that this is a pretty much optimistic estimate of model performance. We need to make it. We need to estimate it on either cross-validated or holdout data set. Anyway, in this case, the performance of the classifier, in this case polynomial logistic, it's slightly better than normal logistic regression. So hopefully by now you see the idea of having changing the threshold and showing the confusion matrix, in this case distribution between correctly classified and misclassified cases, or in this case athletes, and using a receiver operator curve to pretty much visually check it, and area under curve to quantify the performance of the classifier. Another model we can use is a classification tree. So I'm just going to plot it quickly. So it's pretty much similar. You can play with a number of the trees, and this is much easier to use in practice. So this is regression tree, and this is area under curve for a regression tree, and this is a distribution. This is a distribution of two classes based on across the prediction likelihood. Not sure this code works. I'm going to delete this. And another one is fast and frugal trees, which is quite useful package, and give us the, let's zoom this, and give us the really nice graphically output that shows us the tree we got, the data, and the performance. So as I said, we have 3 data points, in this case 300 athletes, 61 injured, 239 healthy, and then the model decided to use training stress balance. Everything over 1.23 is classified injured, and then you can see misclassified cases. In this case, that's 33. You can also read it from confusion matrix. So, sorry, 33 are correctly classified as injured, and 63 healthy guys are classified as injured, in this case after this threshold. So that's slightly different way to show this this classification matrix. You can pause the video and try to understand this a little bit better. So in this case, true, healthy, and injured, and then how is that distributed across the model decision. So these two, 176 and 33, are the correct classifications, and these two are incorrect classifications. So this is false positive, so we have 28 guys in a false positive and 63 in a false negative, as a false negative error. And these two might cost us differently. So that's a topic I'm going to cover next. But before that, let's check the receiver operator curve for this really simple model. So it's 0.64, which is, if I remember correctly, slightly better than logistic regression, but worse than a polynomial logistic regression. Anyway, let's talk more about the cost. So let's say I say that a given guy is going to get injured, and he doesn't get injured. So how much that costs me as a coach, or how much does that cost the club? So let's say that's a cost of 1. It could be financial cost because he's not playing the game, and then we are losing our marketing money and whatever. I removed that guy from training in the games because I said he's going to get injured, but he doesn't get injured. So that cost me, for example, 1 point. And the other error I'm going to make is I call a given guy, no, he's going to be fine, but he ended up being injured. So that can cost me slightly more, or much more, because he's out of the game, he's out of training for a much longer period of time, and that imposes a financial cost on the club, and it's it's really bad on the player as well. So what we can do is we can try to find the threshold that minimizes the average cost. For example, let's say this cost me 1, all these 28 times 1, and these cases cost me 20. So the ratio is 1 to 20. Making this error cost me 20 times more than making this error, or calling the guy injured and he is actually healthy, versus calling someone healthy and he actually get injured. That's much more costly. What we can do is we can try to find the best threshold that minimize the cost. That minimize the total cost, or the average cost, if you divide by the number of misclassified cases. So at the beginning of this script, I wrote the calculate cost, and these are some of the parameters that I use because I calculate the confusion matrix before, but pretty much we give the injury cost, which is how much does it cost me to misclassify someone as healthy and he ended up being injured. So this is 20, so pretty much 20 to 1 ratio. And what we can do now is we can play and see what gives us the best threshold. So I'm going to plot this again. So as I said, it's polynomial fit, and the vertical lines are the thresholds, training stress balance. Threshold zone 1, zone 2, zone 3. And what we want to find is the best threshold. So for example, if calling someone injured, if calling someone healthy and he actually ends up being injured, and the ratio between that type of error and the error of calling someone injured and he actually gets healthy is 1 to 1, the best threshold is 0.52. So we might plot that. So pretty much we are calling everyone healthy, because the cost of calling someone healthy and he ends up being injured is same as cost as calling someone injured and he ends up being healthy. I hope I said that correctly. So anyway, the cost of two errors is the same. So let's say that calling someone healthy and he ends up being injured cost us 10 times more. Let's see what will be the optimal threshold. So in this case, the optimal threshold it decreased to 0.16. So everything over 0.16 we're going to classify as injured, or it's going to get injured. As you can see, there's a really tiny spot in a training stress balance that we're going to classify as healthy, and we're going to try to stay in this particular area. So let's say the cost is 20. So yeah, the best threshold is 0. So we're going to call everyone. We're going to call everyone injured. to minimize the cost. So let's put 15 and see what's going to happen. It's still 0. Let's put 8. So it cost us 8 times more. So yeah, playing with the cost, or it's pretty hard to say how much is it going to cost us, or compare the different types of errors. But you know, pulling out of my ass, pretty much I would say that it cost us 20 times more. It could be even worse. But again, the optimal threshold depends on on 2 things. The first one is the number of injured and number of healthy guys in the data set, and the second is the performance of the model. In the ideal case, all these guys will be separate, and then we're going to have the minimal cost, and most likely the threshold is going to be 0.5. So to wrap this up, the point is that if certain parameter is associated with the injury, doesn't necessarily mean there's a causational relationship, because we didn't implement any intervention. The studies are observational, so it's only associated with the injury. And being associated with the injury doesn't make us being really practically predictive of the injury. As you can see, based on a performance of the classifier using a receiver operator curve and trying to find the optimal threshold based on the costs. As you can see, this is a pretty much famous J-curve that's associated with the injury, but using it in practice is pretty much useless, because the performance of the classifier, receiver operator curve, is around 0.60 something, and everything below, I would say 0.8 or 0.9 is pretty much useless. So hopefully, if we plug in much more data in a model, the model might be more might be better at classifying the 2 cases, injured and healthy, and then we might be it might be easier to select a given threshold and call everyone over that threshold injured, or below that threshold as healthy. So hopefully that gives you some of the idea how the logistic regression works, and making real life decisions based on model performance. And as you can see, this particular model, which is simulated again, but it's similar to the stuff reporting in the papers, is pretty much useless in practice, because even if it's associated with the injury, we are unable to easily say at what point we need to make interventions, and that's something that we need to research more and spend some time, hopefully in some of the future studies. Anyway, thanks for watching. This is Mladen Jovanovic from Complementary Training. See you on the blog. Take care.